Imagine opening a new machine risk assessment. Before you is a blank table, project documentation, a few drawings, a process description, and knowledge scattered among the designer, automation engineer, technologist, maintenance, and safety specialist. The easiest way would be to start by writing a few familiar buzzwords: moving parts, electricity, sharp edges, high temperature. Except that such buzzwords don't make a good risk assessment yet. They don't tell you who is exposed, during what task, in which phase of the machine's life, in which zone, and how harm can occur. And this is exactly where the question arises. Can artificial intelligence actually help an engineer without turning the risk assessment process into automatic generation of random content? Hi, you're listening to the Safety Software Podcast. In this episode, I'll talk about the AI module for machine risk assessment and how it can support work in line with the logic of the ISO 12100 standard. It's worth emphasizing the most important principle right away. The AI module is not meant to replace the engineer. It doesn't state that the machine is safe, it doesn't approve residual risk, it doesn't perform conformity assessment on its own, and it doesn't take over the manufacturer's responsibility. Its task is different. It's meant to help move from unorganized information to a first working draft that a human can check, correct, supplement, or reject. To understand this role well, we first need to recall what the logic of machine risk assessment looks like. The process doesn't start with choosing a safeguard. First, the limits of the machine must be determined. Then, hazards, hazardous situations, and hazardous events are identified. Only then is the risk estimated and evaluated, risk reduction measures selected, and then the risk is analyzed again after applying these measures. Each of these stages depends on the quality of the information gathered earlier. If we incorrectly describe the intended use of the machine, omit an important operating mode, or fail to include a task performed during cleaning, the rest of the assessment may look formally correct, but it won't correspond to the actual way the device is used. The first area where artificial intelligence can help is the description of intended use and reasonably foreseeable misuse. A general statement that the machine is used for processing parts says practically nothing. It doesn't indicate the material, operating mode, user competence, environmental conditions, or process limitations. A useful description should answer much more specific questions. What process is the machine intended for? Who can operate it? What qualifications should the operator have? In what modes does the machine operate? What materials, products, or tools can be used? What user behavior can be reasonably foreseen? What use must be excluded by design, and what must be described in the manual? Based on the data provided by the user, the AI module can prepare a first draft of such a description. This is not a ready-made entry for thoughtless approval. It's a starting point for the design team's discussion and for technical verification. The second important area is machine limits. In practice, this concept is sometimes reduced to the dimensions of the device or the boundaries of the workstation. Meanwhile, limits are much broader. They include the way the machine is used, the intended users, operating modes, and misuse that can be reasonably foreseen. They also include spatial limits, installation site, operating zones, danger zones, access routes, ranges of motion, and connections with other devices. Added to this is the time dimension, the planned life of the machine, the number of cycles, maintenance intervals, wear of parts, and the expected operating time of components. There are also limits resulting from the environment and process, such as temperature, humidity, dust, available utilities, power supply, cleaning method, type of material being processed, or installation requirements. Artificial intelligence can help organize this information into a coherent structure and draw attention to areas that the user has not described in sufficient detail. However, this doesn't mean that it knows the operating conditions of the machine itself. The quality of the proposal always depends on the quality of the input data. The more specific context we provide, the more useful the draft will be. The next stage is creating hazard scenarios. And here, the difference between a general list of hazards and a reliable risk assessment is particularly visible. Simply stating moving parts doesn't describe the risk yet. You need to indicate the exposed person, the task being performed, the life phase of the machine, the location of exposure, the source of the hazardous situation or hazardous event, and the possible harm. One scenario may concern the operator during production, another an automation engineer conducting diagnostics, and yet another a maintenance worker clearing a jam inside the protected zone. The same hazard source can lead to different scenarios depending on the task, operating mode, and access possibilities. The AI module in safety software can prepare proposals for such scenarios based on the data in the assessment. What is important, however, is that the proposal remains embedded in the structure of the documentation. It's meant to be useful in further risk estimation, selection of protective measures, evaluation of reduction effectiveness, and description of residual risk. Every generated scenario requires review. The engineer should check whether the described person actually performs the given task, whether the indicated zone exists, whether the given situation can occur during normal operation, adjustment, cleaning, maintenance, transport, or troubleshooting, whether the possible harm has been described correctly, and whether a similar scenario has not already been included in the assessment. That's why AI proposals in safety software are of a working nature. The user can edit, accept, or reject them. The greatest value is not the generated text itself. The greatest value is shortening the path from a blank field to material that can be subjected to substantive analysis. The team doesn't waste time building a similar sentence structure from scratch every time. They can focus on technical questions. Is the scenario real? Does the protective measure correspond to the indicated hazard? And has the risk actually been reduced after its application? A very important application of artificial intelligence is also supporting the consistency of documentation. In extensive assessments, it's easy to mix up concepts. A hazard source starts to be treated as an entire scenario. A hazardous situation gets mixed up with a hazardous event. A protective measure is entered without explaining which element of risk it is meant to reduce. Residual risk is sometimes described in one word or just by color in the matrix. Such a document may be extensive, but it doesn't show the logic of the decisions. A good risk assessment should allow you to trace the entire line of reasoning. Who was exposed, what task they were performing, in which zone, what hazardous situation could have arisen, what event could have led to harm, what protective measure was applied, which element of risk this measure reduced, and what remained after risk reduction. Such a decision trail is important not only during the creation of documentation. It's also needed for later design changes, audits, machine modernization, and also when you need to explain the basis of a decision made. Artificial intelligence can help maintain consistent language, point out a missing element of the description, or draw attention to the fact that a scenario is too general. Still, however, it is not the final auditor. It doesn't know all the design assumptions and doesn't see the actual behavior of the operators. Let's look at a specific example. Let's assume that the team is analyzing functional tests and machine trials. Based on the available data, the AI module can propose a scenario related to moving elements in the manipulation and positioning zone of the container. An exposed person may appear in the draft. The location of exposure, the source of the hazard and possible consequences, such as entanglement, drawing in, or impact. Another proposal may concern the high-pressure system at the filling nozzle, dosing line, or connection points. A possible consequence could be injection of pressurized medium or impact by an element or material ejected from the system. This is still not a finished assessment. The engineer must verify whether such elements actually occur, whether access to the zone is possible, during what task exposure can occur, and what safeguards have been or should be applied. The difference is that the work no longer starts with a blank table. The team receives an organized proposal for technical review. At this point, the boundaries of responsibility must be very clearly drawn. Artificial intelligence doesn't see the whole machine like a designer, automation engineer, technologist, safety specialist, or maintenance worker does. It doesn't know all the actual operating conditions. It doesn't observe safeguard bypasses used by users. It doesn't perform measurements. It doesn't conduct validation of safety functions. It doesn't check the physical effectiveness of a guard, interlocking device, or light curtain. Nor does it decide on its own whether the applied solution meets the requirements of the relevant Type B or Type C standard. Therefore, responsibility for risk assessment, selection of protective measures, acceptance of residual risk, and technical documentation remains with the manufacturer, integrator, and competent team. The AI module helps prepare material for a decision. The decision is made by a human. So how is it best to use such a tool? First, you need to provide specific context, intended use of the machine, operating modes of users, tasks, materials, access zones, and life phases. Next, it's worth treating the generated text as a draft, not the final answer. The next step is a technical review by people who know the design, automation, process, and actual operating conditions. Only after this can scenarios be linked to the appropriate risk reduction measures. Re-estimate the risk and document why a specific solution was adopted. Artificial intelligence understood in this way doesn't shorten the process by skipping important stages. It shortens the path from scattered information to organized working material. This is of particular importance for complex machines and production lines, where the number of tasks, zones, life phases, and scenarios grows rapidly. In such projects, a major challenge is not only the risk estimation itself, but also maintaining consistency between hazards, protective measures, and residual risk. Let's summarize. The AI module in safety software can help prepare a description of intended use, reasonably foreseeable misuse, machine limits, and drafts of hazard scenarios. It can support organizing language, documentation, detecting missing elements, and maintaining a consistent decision trail. However, it does not replace technical knowledge. It doesn't approve risk. It doesn't perform conformity assessment. It doesn't relieve the manufacturer of responsibility for machine safety. Well-used artificial intelligence is not an oracle. It's an assistant that allows you to reach a better organized and defensible engineering decision faster. It can be put most briefly in one sentence. AI supports, the engineer decides. You can find more information about the module on the safety software website. You can also set up an account and check how the tool supports the preparation of working descriptions and scenarios for further review. Thank you for listening to this episode. Goodbye.